Hello guys, in the previous video I managed to get the Advent of Code 2024 Day 8 Part 1 completed, and in this video let's continue the Part 2. So without further ado, let's check what kind of challenge we have waiting for us. So in the Part 1, just to recap, we need to calculate how many distinct, unique locations we had for the antinodes, so these hashtags. And in the part 2, what we need to do. Watching over your shoulder as you work, one of the historians asks if you took the effects of resonant harmonics into your calculations. Whoops! After updating your model, it turns out that the antinode occurs at any grid position exactly in line with at least two antennas of the same frequency, regardless of the distance. This means that some of the new antinodes will occur at the position of each antenna, unless that antenna is the only one of its frequency. Okay. So these three T frequency antennas now create many antinodes. Okay, interesting. Let's actually create Day 8 Part 2 already here, and this is one type of field. Yes. So these three frequency array antennas now create many antinodes. Okay. In fact, the three T frequency antennas are all exactly in line with two antennas, so they are all also antinodes. This brings the total number of antinodes into the above example to 9. The original example now has 34 antinodes, including the antinodes that appear on every antenna. Okay, so what we need to do is that we'll get the updated example map and example map, which is this. And now we remember to split it up for rows, and then we can run it. And then what we want to do is we need to refactor this calculate antinodes function. We can rename this multiple antinodes. So basically we need to calculate every antinode, not just these two, which will be within the map. Okay, so I have one brute force solution in mind, includes while true. So we could just have two while true loops here, which will calculate new antinode positions for us. And if we go to else, so it is going beyond the map, we will then break the loop. And same for here. Then else break. Then we can remove these, and I think we should be okay. We can try to run this. We can copy this code here, update the function name that gets called, and then we can print the unique locations after that. But let's run and see how it will behave. And actually before that, we need to, let's copy also this code so that we have the same thing here next to each other. So example map, we can do that, and then let's run that once more. Then this, it will most likely run slightly longer than previously. And actually, now I realized that we made a mistake. So it will constantly calculate the same antinodes. Not a good idea. So we need to first calculate the antinode, and then calculate the antinode 1. So we need to have the previous antinode existing, so we can calculate the kind of next antinode from that. Or the other way we could do it is that we double this diff every time. Actually, that kind of feels somewhat more cleaner solution. So if we have the antinode 1 increment, so basically this holds the value of how many times we will increment. So xdiff is xdiff times antinode increment 1, and in the first iteration we want to just have the initial value, and in the future iterations we want to have the proper, and we can just double this every time, and then we should be able to do the same for here, and just oops, not there, instead here, and then we can just xdiff ydiff, and now it should behave a bit better. We need to also remember to update the increment, and so now we think that we get first a kind of initial difference, and then we multiply it until we go beyond the map area, and then we will just return the antinodes. Yes. So if we run that, it should go good. Then if we run this is so small map that, oops, we need to use the example map. It's a limit there. And this takes so long that I'm wondering that where we are in stock. Yes, that I need to also fix potential. So this run now very fast. So we have how many? We have 10, but this says 9. Okay, let's see what is the difference. So we have x2, y4. Yes, correct. Then x3, y4. That's incorrect. There is nothing there. 6, x3. Okay, that's correct, yes. Then, oh yes, now I actually, it's not doubling. Or actually, yes, it is. Yeah, that was correct. So this is not correct, but this is correct. And then we should have this x. So this is not anywhere. 3, 4. So something is not that using the old one. That makes sense. So now we have 6 in the map, but we have only 5. Let's double check that art is correct. So x2 and 4, that is correct. Then 3 and 6, yes. And then 5 and 0 for 1, 2, 3, 4, 5 and 0, yes. Then x6, y2, 2, 3, 4, 5, 6. What? No. 2, 3, 4, 5, 6. That's correct. And then 7, 8, 9, and 3. Yes. So this was the only one that it couldn't calculate. And do we have still some like problem that we are not calculating? Actually this should be +1, I think. Now we have 6. Okay. Yes. And the last one, x 1, 2, 3, 4 and y8. 1, 2, 3, 4, 5, 6, 7, 8 is here as well. Wonderful. So now we can proceed with the actual input that we have. And then we can rerun this and then switch to input. And then if we just check how many we have quite many, and how many unique locations within the bounds of the map contains an antinode. So let's check the length of this set. 1157. Let's check. Does it look correct? That's not the right answer. Your answer is too low. Curiously, it's the right answer for someone else. Yeah, that was just pure luck. But then let's rerun the more complex map. So this one are exactly in line with 2 antennas, so they're all also on the nodes. Aha! So we have something missing, not missing, but so we are not handling in some case. After updating your model, it turns out that the antinode occurs at any grid position exactly in line with at least 2 antennas of the same frequency, regardless of the distance. This means that some of the new antennas will occur at the position of each antenna, unless that antenna is the only one of its frequency. Aha! So in this case, 3 frequency antennas are. So basically, if we would modify this so that if frequency locations are 1 or more than 1, we can then count the antinode locations, them as antinode locations. So if, let's check, if length of frequency locations is more than 1, we can just for frequency locations, we can just run antinode at double of dot x and then double y. Let's now check also that what we will get from the original example set that we had. Let's convert that as well. Not supported between instances of list and int. Oops, yes, my bad. And then, yes, okay, we get 9. So now if we would run this against our original input. So we got 9. So now if we would run this against our original input, and then let's run that, then this, and then this, and then so previously we got 1157 and now we got 1285. Okay, that was relatively easy as well. So we managed to get the day 8 now completed. It wasn't that difficult in the end. I was a bit surprised how smoothly it actually went, but it's interesting to see that what is waiting us or in the next day 9. But I think it's good to stop here the video so that it won't get too long. Thank you for watching and see you next time. See ya!